All right, so today we're just going to finish up with linked lists. We left it off last time where we had a bug in our linked list implementation. Remember that we were adding all these elements, and ultimately our remove element at index worked on most cases, but it didn't work if you removed it from the head. So to remind you of what this looks like, again, we were adding a bunch of stuff. We started out with 10, 20, 30, 40, 50. Then we manipulated it. We ultimately tried to remove 101, and it doesn't work. It removes 10, the second element, instead of the first element that we intended. So now I want to actually, to suss this out a little bit more, and I'm going to set a breakpoint here, and we're going to go ahead and go into debug mode. And I am now here. What I'm going to do is I'm going to step into that function to see what's going on here. Remember that we're removing the element at index 0. So when I do that, I come in here and I'm trying to remember that index is 0. We're trying to remove the element at index 0. And so I'm trying to get the node at index 0 minus 1, which is -1, right? And so if I step into that, I see why I am getting the wrong results here, because there is no element at index -1, right? I'm not getting an exception though, because I'm not checking for an exception here. And if I step into get node at index, which is a private method, right? Then index is -1, right? We initialize current to head. And so if I step here, then this for loop will never execute. And we end up returning current, which is removing the head, basically, right? And so when we get down to this, it's going to work perfectly fine because you're removing the head. Yeah, previous ends up being the head instead of nothing. So I'm going to go ahead and stop this. And let's go back to the Java mode here. And this is one of those times where the corner case, where you might have an argument here for ensuring that you do have this different method here of not add elements to the head, but do we have a remove element at head? Oh no, we don't even have one. So what I'm going to do is if index is equal to 0, I'll make this a special case where I remove from head, right? Okay. And that's going to be a little bit different than removing an arbitrary index or the last element or something like that, because that involves updating the head element of the entire list. Okay. I don't have that function implemented yet, so let's go ahead and implement that now. Public remove from head. Public void. There you go. Just double check to see this is running. Yep. Okay. All right, so how do we end up implementing this? Oh, good point. Do we want to return the element that we ultimately remove? I think so, because here we're going to end up having to remove it. So I'll change the signature of this to return whatever we're going to return there. All right. So if I'm going to remove from the head, then I need to save off that element, right? Tx is equal to this dot head dot get element, and then ultimately we're going to return x. But before I do that, I need to make sure that I am getting rid of the actual head node here. Okay. Now to do that, again, consider that you've got this list here, right? It goes on whatever, dot dot dot, and we have this reference to the head node. Okay. So to remove that head node, what do I need to do? I need to get rid of this one. All I need to do is make head point to the next node, right? And that effectively deletes this element right here, because all we have to do is point head to the next node. So this dot head is equal to this dot head dot get next. Okay. Let's try that out over here in the demo and see if it works now. Remember that we were trying to remove 101, and it now works. Right? Now we're removing the element at index 0. That ends up being 101, and now we're left with 10, 20, 142, and the rest of them. Right? So simple enough fix there. Couple of other things that I would want to do is maybe a contains, or a linear search implementation. Public Boolean contains. And here we'll have the element, I'll just call it x, right? And this will return true if x is stored in the list, false otherwise. So let me go ahead and try with an initial basic for loop here, right? So for int I equals 0, I is less than this dot size. Ooh, you know what? Now that reminds me, I plus plus. If I'm removing something from the head, what should I do? Size minus minus. Right? Now I'm taking care of that right here as well, except that I'm not taking care of it right here. Right? What should I do? It's dot size minus minus. There we go. I forgot both of them. That was another bug. I should have been testing. Okay. We'll find out if there are any more other bugs here in a second. Okay. But otherwise, what I'm going to do is I'm going to get the node. The ith node is equal to this dot get node at index I. Right? And then I'm going to ask, is the thing stored in the ith node, is that equal to x? So if ith node dot get element is equals to x, then return true. Otherwise, if you get through everything, return false. Now, is this how you go about testing for quality for objects? Would this work if it were strings? Does equals work for strings? No. It works for integers, but that's because of auto-boxing and unboxing, right? And it'll end up treating them as numbers, and then equals is perfectly fine. We don't use equals. What do we use? Dot equals. And if the element is equal to x, then we return true. Now, what's the implementation of that equals? Well, it depends entirely on what type it is. If I were to click on this, it'll just take me to the generic object here. And then what's the equals? What does it look like? Okay. Go back. Back. Equals looks like this. It is the equals, but that's the default, right? How does strings dot equals work? Yep, strings dot equal, or I'll do here, string dot, and let me go ahead and just go to that class and find out equals, right? Well, it does do an initial equals, because if they are the same thing in memory, then yeah, they're going to be the same. Otherwise, it goes and it checks for every single character. That's what this function is doing here. String.latin1 equals. All it's doing is going over each and every single character and making a check. Is it equal? Is the ith character equal? And if not, then it returns false. Okay. So equals is what we want. Okay. Let's go ahead and test it. So what's in here? 42. System.out.println. We've removed, what did we remove? 101. So does it have 101 and does it have maybe 42? We'll ask both of those questions, right? And this should be false because we've removed 101, and this should be true because 42 is still in there at the end. Oh, yep, thank you. What is it? Foo.contains. Thank you. Sorry. And then 42. So it should be false and then true. Excellent. But now, let me go ahead and come back to this thing up here. And let's go ahead and add n elements, where n is some value here. Int n is equal to, so let's just say 1,000, right? Add elements to the start of the list, add element to head. Remember, we made this, we witnessed that this was inefficient to begin with, and then we made it efficient. What I want to do now is, let's not do random values. Let's actually do predictable values here. So for int I equals 0, I is less than n, I plus plus. we're going to end up adding all of these i's to it. The last one that we add is 999, so it'll be 999, 998, 997, etc. in the list. Save. What are you complaining about now? System.out.print. Oh. Opening curly bracket there. All right. Let's run it and see that it indeed is going to be 999 all the way down to 0 at the end. Okay. Now let's search for 0. Right. System.out.println foo.contains 0. In other words, I'm doing a linear search and I'm going all the way down to the end to find that it's there. Okay. I don't. That's what I want. That's what I want to end up timing. So let me go ahead and move all this stuff over here. I don't care about actually adding stuff. There, it gets in there. If you want to, we can go ahead and go with system.out.println done adding stuff. All right. And then what we're going to do is we're going to time how long it takes to search for that last element. Right. 4 milliseconds. True. And let's stop printing it out here because I don't care. Right. If I go up to 10,000 elements and search for 0, which is going to be at the end, let's find out what that looks like. 4 milliseconds. Now we're increasing it tenfold. Oh, wow. It's, what, 25 times slower? Something like that? Okay. 10,000 up to 100,000. Predict how long this is going to take now. This is 0.1 seconds. I'm increasing by a factor of 10. So it's actually going to slow down by a factor of 100. It's actually going to take about 10 seconds because 0.1 seconds times 10, 100 is going to be about 10 seconds. It's between 5 and 10 seconds here. There we go. Yeah, more than 10 seconds. Okay. If I go up to 1 million, what do you think? Again, it's a tenfold increase. It's going to be 100 times slower. So 10 seconds times 100 is going to be 1,000 seconds. How many is that? It's like 20 minutes or so, thereabouts. Done adding stuff. It's still going to go, 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 go. Why? Why is this so inefficient? Because what? It's the linear search to the end of the word list times the size of the list. Right? Remember the painter? Right? Always walking back, always walking back. To get the ith node, we're calling this function over here. What does it do? It starts at the beginning. Right? It walks all the way back to the beginning of the fence and then goes all the way to the ith element. If there are 1 million elements in there, right, it's going to start at the million at 0 and go all the way to the million just to give you that element. Right? So you're doing this millions times million. Right? We call them trillions. Right? And that's why it's not efficient here at all. What should I have done instead? Pick up the paint bucket with you and move along with it. So not this for loop here. Instead, let's keep track of the ith node. I'm just going to actually grab this. Right? Ith node. We'll start it at this head. Right? And while the ith node is not equal to null, in fact, I'm going to rename this. I'm going to rename this the current node. Then I will make my check on whether or not the current node's element is equal to x. If so, break out of the loop and you're done. Otherwise, go on to the next one. Current is equal to current dot get next. Now, remember that this would have taken, I estimated at 20 minutes or so. Done in 12 milliseconds. That's a huge difference, right? That's a difference between linear and quadratic. Right? Okay. One last thing. It was asked today, and I planned on doing it here in this section anyway. It was asked today, well, wait, when you use these regular things like, say, a list of strings, right, names, right, you can use an array list, right, new array list. So in other words, you don't need to make your own array-based list in practice. Of course, you shouldn't in practice. Let's go ahead and import it, and import the list. And you can go ahead and use it in an enhanced for loop. So for string s in names, you can go ahead and say system.out.println s, right? You can use this in an enhanced for loop. How? How could we make our list be usable in an enhanced for loop? Likewise, a linked list is also supported in Java, right? You don't have to roll your own. In fact, you shouldn't roll your own in practice. Now, fast forward to your second to last assignment where you have to make a sorted list class. Yes, you do have to make your own list. You can't use our linked, or you can't use Java's linked list. You can't use the Java's array list, okay? But one of the parts of the bonus there is how can you make it so that your linked list or your array list or whatever is iterable, right? In fact, that's what it is. Implements iterable. There we go. And it iterates over elements of type T, the same stuff that it holds in here. It wouldn't make much sense if it were, say, it held strings and then you iterated over it and you got integers. That's what? Right? That doesn't make sense. So restore it back to both of these T's here. Now, because I'm implementing iterable, that means I have this one method that I have to implement. It's down here. Right? You have this method called Iterator that returns this Iterator object. This object, you can ask questions of it. You can say, hey, Iterator, is there another element that available that I can go to next? And if so, go ahead and give it to me. Right? Those are two methods. Do you have another next? And give me the next. Okay? And let me go ahead and go with a return a new Iterator. This is an anonymous inline class declaration. So what we're going to do is we're going to create this iterator and define it immediately here. Now I have to implement two methods, like I said. Do you have a next? And give me the next. How do those work? Well, they're going to work exactly like our loop that we just wrote, this while loop up here, right? We're going to start at the head, and then while the current node is not equal to null, then of course you have another next and you would execute this while loop once more. Right? But you also need to set it up so that the next time you ask the question, do you have another next? You have an answer for it. And so we're going to go to the next. Okay? What I need to do is I need to create a variable to keep track of that stuff. I need a node, t, current, is equal to, I want to get the list's head. How do I get that? This dot head? What is this referring to here in this context? Let me click on it. It's referring to this iterator right here, right? Not the list. But that's okay because we are creating this thing inside the class. It's somewhat like what's called a closure, right? So you're within a closed environment, and you know that there's this thing called head, and what's its scope? Well, it's inside this class up here. It's not exactly a closure, but it's kind of like a closure, right? Don't worry about that. It's a functional programming kind of thing, okay? So I set this up so that the current node is equal to the head. Now, do you have next? Well, it depends. I have the current node in my hand now, right? Is the current node valid? In other words, is it not null? So I return this.current is not equal to null. Now the this keyword is referring to the iterator that I'm creating right here. Okay. If it's not null, then I have something to give to you, the thing that I've got in my hand right now, the node that I've got in my hand right now, right? If I've gotten to the end of the list, then my hands are empty. I don't have a node anymore, and so I return false. Right? Now I actually have to give you that thing, that node in my hand. So return this dot current. Well, that's not going to work. Why? This dot current is what? It's a node, right? And you want to return to elements of type T. So dot get element. Right? Except that I'm not setting myself up for the next iteration, right? Here's my node. I take the thing out of it and give it back to you. But what do I need to do now? I need to take the next element and put it into my hand so that the next time you call next, I have the next node to give to you. Right? So I need to say that this dot current is equal to this dot current dot get next. Except that if I advance before I get the element, I've lost the element. So store that off into a variable, right, so that you can return x. Now what type is x? T. And again, polymorphism at work here, right? A local variable, what's the type of the variable? Integer, string? Yes, all of those things, whatever you want. I think that I've got a more current version of Java here, so I wonder if var will work. It will. Awesome. Let's write. Let's put in a brand new feature to Java to save on some typing. Except what? I've traded one character for 3 characters. Yet another reason that feature that was added was stupid. Okay. All right. So let's check this out and see if it actually works. I don't want to have a million. I want to print a million elements. Let's just print 100 elements. But I can go into a loop here for integer in the collection x in the collection foo. System.out.println x. Compiles because it's iterable, and it works. Right? It went 99 down to 0. Okay. So questions on linked lists? Is there anything else that we want to do as far as this list is concerned? This list, we've got a linear search-based contains method, add element to head, add element to tail, remove from head, remove element at index, get element at index, get element, get a private get node at index. Looks pretty good. Of course, you can add bells and whistles on later on if you really want to. Yep, there we go. Okay. There are some variations. Let me go over to my notes here. There are variations. You can keep track of both a head and a tail element to simplify some things, simplify some operations. You simplify some operations, you end up making other operations more complex because you have to do the bookkeeping on 2 nodes now. Okay. You also can have what are called doubly linked lists, right? Where you have both a previous or a next and a previous. And I'll codize that. There we go. And here's the visualization of that. So you see that each node here has an element, but it also has now 2 references. The previous and the next. Previous and next. Previous and next. Right? You can keep track of the head and the tail, like we said before in a variation. But this allows you to traverse 2 ways. You can traverse left to right, but now you can also traverse right to left. And that has an advantage of simplifying some operations. For example, if you get this element here, it's easy to get the next one, the next one, the next one. It's not so easy to get the previous one unless you're keeping track of the previous one. So you save on some bookkeeping in some regards, but then, of course, now you have to keep track of both a previous and a next. So to insert something, it would be a little bit more complicated, right? It would end up being, if I want to insert it right here, I would have to make sure that this one points here, that this one points here, that this one points here, and that this one points here. So if you're doubling up your references, you're also doubling up your reference shuffles. Right? Worth it? Not? I don't know. It depends on your use case. Right? You can also have circularly linked lists. Right? Circularly linked circularly linked lists. There we go. That looks like this, right? So you don't really have a head. Instead, what you have is a current, because there is no start of the list, there is no end of the list. When you get to the end of the list visually here, it just wraps around back onto itself. Right? In other words, it forms a circle or a ring or whatever you want to call it. Right? The current would then, traverse this list. You'd have to keep track of, have I been here before in some manner? Right? If you want to iterate over all of them, then you need to know that there are 3 elements in there, so that I go next, 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 and I'm back where I started. Otherwise, I'm going to get stuck in an infinite loop here. That might be a useful data structure if you need to go round and round on something for some reason. Old school token ring networks used to use that, right? Has anybody ever been to a LAN party for games? Okay. All right. And nowadays, I'm sure, did you connect wirelessly to each other then? Or did you actually plug in? Yeah, okay. You used Ethernet, you used Cat5, and you all went into the same router. And that router, everybody goes into one router, and then that handles communication back and forth. It used to be that you had, when you had LAN parties, you would set up a token ring network. And it's not Cat5, it's this coax-looking stuff. Computer A, computer B, computer C, and then computer C would then go back to computer A, so that it was a complete cycle, right? And that's how the token ring network worked. You just go around, and each computer on the network would get a slice of that network, right? And that's one data structure that you could use to manage this, right? That idea, at least. Okay. You also have what are called unrolled linked lists. Unrolled linked lists are kind of a marriage of these two things, where you have a linked list, but you also have an array-based list inside of each node. Looks kind of like this. So each one of these things is a node, right? Oops, that's not what I wanted. There we go. Each one of these things is a node, but each node now holds an array of elements. Each node does, of course, go to the next node, but that node also holds, say, m elements. And then over to m elements, right? A linked list is exactly an unrolled linked list with m being 1, right? Where you only store one element in there. And the nice thing about this is that you can tune it to whatever your memory needs are. For example, you could make m exactly the size that you need to store in a page of memory or something. And then that will help reduce cache hit misses, right, and increase cache hits. That this entire section of the list gets loaded up into memory instead of piecemeal, just one at a time being loaded in memory or something. Right? Less memory fragmentation if you marry these two ideas together. And that's called an unrolled linked list. You also have yet another variation called skip lists. Skip lists. And the idea here is, let me just go ahead and draw it. Here's a regular linked list, right? You're going from node to node to node to node. Now, to get from here to the end, you would require 1, 2, 3, 4, 5 traversals. Think of this as a subway in a major city, right? Each one of these stops on the subway is what's called a local, right? If you get on the local train, it'll stop at every single stop along the way. Or you could get on the express. And the express doesn't stop at every stop, it just stops at the major stops, right? So you could go ahead and skip those 2 stops and jump right to this one. And then if you need to go to this one, then of course you take the local train to that stop. Otherwise, you might have like 2 skips here, right? Maybe even you have one large skip or something, right? And it allows you to basically traverse a linked list much faster in practice but of course it's, the cost is that you now have to maintain all of these skips, right? And it's a much more, not daunting task, but it's a much more involved task, right? This is called a DAG, by the way. Directed Acyclic Graph, right? And you'll get into graph theory eventually, but this is a DAG, right? Why is it acyclic? Because you never go back, right? It's directed. Why? Because you only go forward, right? And it's all connected. From the start, you can get anywhere. Sometimes you can get to places faster by jumping and skipping things. That's why we call it a skip list. Right? At some point, of course, if you add too many skips, guess what? Yeah, you're back to square one. You're basically even more complicated than an array list, right? And you've lost all the advantages, right? So it's a balancing act, right? And of course, the other variations are going to be restricted access data structures, namely a stack and a queue. Right? And that's our next topic here, is subtopics. It's within the same module here. So you've seen stacks before, and we've talked about queues a little bit before. But the collections that we've seen so far are unstructured. Right? They are data structures, but they're unstructured in that lists have orderings. Right? There's a first element, second, dot, 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 last element, etc. But lists are not necessarily sorted. There is a difference between ordering and sorting. Right? If I had a list containing elements, say 10, 5, 30, 4, and 8. Right? If that were an array-based list that looks something like this, dot, 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 there is an order here. There is the first element at index 0, the second element at index 1, third, fourth, fifth, right? There are ordinal elements, but does that look sorted to you? No, right? So there is a difference between order, and sorted, right? So even if we were to sort a list, it would be imposing a structure on the list's state. So you can do that, but it doesn't necessarily mean that it's a data structure. I mean, it is a data structure, but it doesn't necessarily mean it has a lot of structure. One way of getting structure, one way to design a data structure with structure, is to limit the access that the outside world has to it, and that's where we come with a where we get the idea of a restricted access data structure. We impose an ordering on the collection's behavior, right? And that's what stacks and queues are. Stacks are a FIFO, and queues. There we go. Still spelled it wrong. Are a backwards. LIFO and FIFO. Right? So do we remember what LIFO stands for? Last in is the first out. Well, what is FIFO then? First in, first out. Right? And by limiting the access, the way that you can interact with this data structure, that's how we've given these things structure. Okay. That structure can then be exploited for efficient algorithms, or going back to, again, the theme of one of the themes of this course is smart data structures and dumb code are a lot better than the other way around, right? We're going to have more smarter and smarter and smarter data structures as we go along here. Right? So as we've already stated, the stacks is a LIFO data structure, last in, first out, right? the last element to be put into the stack is the first element that comes out of the stack. And the two operations that we're going to focus on are push and pop. Right? Again, I've tried to look historically at why they're called push and pop, and the only thing that I've ever been able to come up with is a stack was created in the context of computing in the 40s, I believe, or 40s or 50s or something. But in any case, the only one that I've ever come across is the analogy of plates in a cafeteria, right? You don't stack. You do stack plates, but you don't stack them up to the ceiling. It'd be difficult to reach. So in your cafeteria, where are the plates? They're in this thing with a spring load, right? And you can push it down on top of it, and it pushes it down, and the spring goes down a little bit, right? And what happens when you take one off the top? You pop it off the top, and you get and then the spring loaded, the spring mechanism pushes the next plate into position, right? So push, you're putting it on top, and pop, you're popping it off the top. Push makes sense if you're pushing something down, but pop, I don't know, it pops off the top. Don't ask me where somebody got that verb in that context, right? So let's go ahead and use a basic implementation. Suggestions? Why don't we use a list? Right? Why should we have to reinvent the wheel? I'm going to close all of those and collapse this. Let's go ahead and create a new class called a stack. And I will parameterize it so that you can put whatever you want onto the stack. Okay. Now, instead of using my implementation of a list, let's just go ahead and use Java's implementation of a list. Private list T, right? And I'll call it, I won't call it S for stack. I'll just call it underlying list. There we go. So let's create a new stack. Public with a constructor, stack, and this dot underline list is equal to new. Do you want to use an array list, or do you want to use a linked list? Which one? Well, with a stack, visually, all we really need is one end, right? Here's my stack. Oh, come on. Not a parabola. Okay, that's good enough. It's ugly, but whatever. If I push, say, 10, 20, 30, right? You push things in, you pop things out. Do I necessarily need access to the guy down here? No, in fact, if I did, that would be breaking the stack. If I was able to take that out of the stack, and all the dishes now fall over, right? So I really only need one end. Say, what if this were the head, and this were the tail, and they were linked together like this? And then the push operation would be add to head, and the pop operation would be add or remove from head. So maybe a linked list. There we go. I need to import all of these. Import, import. There we go. Now let's implement those two operations. Public push. So we're going public void push. And we're going to take an element of type T, and we're going to push it onto the stack. And public void or T pop, because we are going to return it, right? And it returns the element on the top of the stack. So how do we push with our in terms of our underlying list here? This dot underlying list dot add We could add it to the end of the tail of the head, right? It's the same thing as tail and head and tail. As long as we're operating on one end or the other. Dot add. If I'm going to add it at the end, then where do I need to pop it? Return this dot underlying list dot remove. I don't know, removes the first occurrence of the given object. That's not what I want. Remove the element at some index here. Remove, and what index do I want? This dot underlying set list dot size -1 because of course it is 0 indexed. 5 elements, 0, 1, 2, 3, 4. I want that one right there. So here I'm operating on the end of the list. What would it look like if I operated on the beginning of the list? Dot insert or add at index 0, x. And here I could simplify this to always remove from the 0 index. Right. All you have to do is be consistent about it. And by the way, you can use an array list, but you do have to be careful because if you're operating at one end, then you're doing a lot of shifting. But if you're operating at the other end, you're not doing any shifting. Right? So if I'm going to use an array list, I would want to go back to the original version that I had where I was working on this end over here. Okay. So let's undo that and go to the linked list. Linked list is efficient on both ends, by the way. Let's take a look at Java's linked list implementation. Guess what? It keeps track of a head and a tail. And what does it do? How does it implement those things? A node. And what does the node look like? Come on. For this is a linked list node. First and last in this case are previous and next. Right? I don't know why. No. Oh, sorry. No. That I'm still in the same. Find linked list node. I shouldn't have scrolled all the way up. Come on. I want. And there we go. Okay. There. That's what I want. It keeps track of the item, but also it keeps track of the next and the previous. So what kind of linked list do we actually have here? What variation? We have a doubly linked list, and we're keeping track of both a head and a tail operation. Right? Okay. And guess what? It's made private, so that you can't screw around with it. Right? All right, we're always operating on the same end. Let's go ahead and test this out. So let's go ahead and create a, what do I call it again? Stack of integers. S is equal to new stack. For int I equals 0, I is less than, say, 5, I plus plus. S dot push 10 times I. And then we'll do the exact same thing, but we'll go ahead and print out what we get. So system.out.println s.pop. So what order am I putting these things in? I'm putting in 0, 10, 20, 30, 40. What order should I get them out in? 40, 30, 20, 10, 0. Yep. So it looks like it works to me. What happens if I try to pop from an empty stack? Index, what are you talking about? There's a stack here, right? Okay, so let's fix that. First of all, let's add some convenience functions here. Public boolean is empty. Right? Return this dot underlying list if dot size. If that's equal to 0, then the stack is empty, right? And so if this is an empty stack, then we'll return question mark, question mark, question mark. What could we do if you try to pop from an empty stack, it could give you nothing. So return, nothing is null, right? Now, that design decision has a consequence. Over here, am I allowed to push null? S.push null. Yes. How do I know the difference between there's nothing here, so I'm going to give you null, versus you pushed null some time ago, and now you're popping it back out? Valid, invalid. Right? So by returning null, maybe we want to restrict it so that if they ever try to push null, if x is null, then, I don't know, throw on illegal argument exception with the error message, this stack doesn't support nulls. There we go. And bring that in. I spelled it right? Illegal argument exception. Throw new illegal argument exception. I shouldn't have to import that. That's part of java.lang. And there we go. All right. So the stack doesn't support nulls. My attempt to push it null here failed. Okay, fine. And now I should get back, 40, 30, 20, down to 0. But then at the last one, it should be null. And that's my flag indicator value to say that that's an empty stack. Right? What's an alternative? If it's empty, we could throw another exception, right? Throw a new illegal state exception. Right? Cannot pop from an empty stack. Okay. And that's our design decision over here. Right? We made sure that you have access to this empty method to look before you leap. So it's on you now, right? You can't pop from an empty stack. You should have asked, are you empty or not? In other words, you should have had a loop that didn't look like this. You should have had a loop that said, while S is not empty, go ahead and pop, 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 pop. And that looks much better. Right? Yeah, okay. I just needed to make sure that everything is in frame. I should have done that before, sorry. Okay. What other operations? Those are the only two core operations that you need, push and pop. What are some of the other operations that would be nice to have? Okay. Public boolean int get size, return this dot underline set dot size. Yeah, there you go. That would be nice to have. How many things are still in it? Right. Another one is a common operation called peek. Right. Public void t peek. Right. So what is peeking? You can just peek at it, but you're not going to actually remove it. Right. So it returns the element at the top of the stack, but does not remove it. How would I end up doing that? Well, to pop it, I say remove the element at index 0. So return, don't remove it, this dot underline list dot get the element at the at index 0. Right? I'm not removing it. I'm just here's what it is. Take a peek at it. Right? Okay. What's another design decision that we could, think about? So if you have a call stack and you have function calling function calling function calling function, what eventually happens? Remember, how does that work? A function calls a function calls a function calls a function. These things called stack frames are created. Eventually, what happens if you do that too much? Stack overflow, because you have a limited stack. So we could implement this so that we have a limited stack size, right? Private int max size. Okay. By default, what we could do is we could set this dot max size is equal to -1. That flag value will tell us that it's an unbounded stack. They can go ahead and add as much crap as they want to the stack as they want, right? But if it's if they provide it, say a different constructor here, public stack int max capacity or max size, right? Then we'll say that this dot max size is equal to max size, and then we'll initialize our list here. There we go. There. Okay. That means that I should be calling that other, this, -1, and that's it. There we go. Okay. Now that we have this max size parameter, I have to be careful, right? So if you're about to push something, first of all, we're not going to allow it to be null. But also if this dot is full, right? Then I will throw a new illegal state exception. Stack is full. You can't add anything more. Right? Well, what would that look like? Is full. Look kind of like is empty. Public boolean is full. Return this dot underline list dot size is equal to max size. Except this is where we put that logic, right? What if the max size is -1 and there are 10 things in there? The interpretation of the max size of -1 is that there is no bound, right? So we'll say if this dot max size is equal to -1, then return false. It's not full because it can never be full. It's called an unbounded stack. You're not putting a bound on it.
Return false.
Oh, good point. So max size is 10 and the list, yeah, I like that. Okay, there, simpler code. We don't need that. If it's -1, then it'll never be satisfied, and so we're good. Yeah. In fact, I'm going to go back and make sure that's final, period. Right? Don't change it after you've set it. Okay. Peak would not change. Pop would not change unless, you know, you get down to 0, and we've already taken care of that here if it's empty. Let's go back over here to demo and test it. If I create a new stack that can only hold 4 elements, I should get an exception here on the last iteration. Yep, stack is full. But if I make it so that it's at most 5 elements, then all 5 of them work. I like that. Unbounded. There, that's good. All right. Should we allow somebody arbitrary access to stuff? Public, void, remove element, remove bottom element. Right? So in other words, that's like allowing somebody to jump all the way down here to the tail and removing that element. If you want to, but is it really a stack? Not really. We'll see how Java does this. Java uses what's called a deck. And it uses lists anyway, and it lets you, here you go, here's a list. You can use it however you want. You can use it as a stack, you can use it as a queue, you can use it as a deck. That's on you. We're just going to give you access to everything. Right? So probably not a good idea in our own implementation to do that, though. Okay. All right. So we'll conclude here by talking about a few of the applications of stacks. Basic implementation, a list-based data based implementation. Right? Applications. Well, we already mentioned one application. It's going to be a call stack, right? Programs have call stacks to keep track of where they have been. In other words, function A calls function B, calls function C. How do you return back to the calling function efficiently? Through that call stack. You left breadcrumbs. I went from A to B to C. To backtrack, all I need to do is go in that line again. Right? And if I need to, I can go down to another different path by calling a different function. Right? Generally, stacks allow you to keep track of breadcrumbs. Why do I use that analogy? Hansel and Gretel, right? Why did they put down breadcrumbs? They knew how to get back out of the forest, right? They knew where they came from, right? And that's used in graph traversals. Right? For tree and tree traversals. With graph traversals, we're talking about an algorithm called DFS, which is depth first search. Right? And tree traversals are just special applications of DFS. You have what's called pre-order, in-order, and post-order traversals. We're not going to talk about general graphs here, but after we get done with algorithms and algorithm analysis, we will be talking about binary trees. And we will be implementing pre-order, in-order, and post-order traversals on those binary trees as search algorithms on trees. Okay. Stacks allow you to simulate recursion. Right? You don't have to abuse the call stack. You can go ahead and create your own in-memory stack and simulate the recursion so that you're not hitting those stack overflows. Right? And if you have an in-memory allocated on the heap stack, you have way larger stack size than you would if you use the call stack. Right? You can also, there's the shunting yard, backtracking algorithms, backtracking optimization algorithms. You also have what are called the shunting yard algorithm. There we go. Does anybody know what a shunting yard is? Usually there's one or two people that have a family member that works for UP, Union Pacific Railroad. No? Okay. Shunting yard. I wonder if we can pull up a photo of it. Well, that's the algorithm. Images. All right. That's kind of a, yeah. Here's an aerial view of a shunting yard. So why does it have so many paths? If you've got a very long rail cars, right? And this section is going to Chicago, this section is going to New Jersey, this section is going somewhere else. What you do is you back the entire thing up, you sever the connection to where these cars need to go to one direction, you pull out, and then you pull in another car to hook up to it and then go on, right? So you need these shunts in order, an entire yard of them, to be able to back things up, store them there, and then move on. And a stack, these are basically stacks right here, right? Because you're not taking individual cars apart and moving them around, right? That's very, very difficult to do. Right? And so there's a shunting yard algorithm that you can use for a bunch of stuff, right? Otherwise, that's stacks. We only have 15 minutes left, so I'm okay or ending earlier, but queues, right? So queues are FIFO, which is, again, first in, first out. Right? What do you think about the implementation here, though? If I've got a line, here's the head of the line, here's the end of the line, right? Where do people enter the line? At the end of the line, right? Unless they butt in or something like that. And who's the next person to get served? The one at the front of the line, right? So, same thing, list here. Maybe a linked list, where you dequeue things off of one end, but you enqueue them, enter them at the other end. Sometimes this is called pull or offer, or push or offer. Sometimes this is called poll or POLL or DQ. Right? And we'll look at all the variations there when we get back, right? And applications of queues as well. But very easy to implement both stacks and queues using a simple list implementation here. Right? By the way, what powerful, or not powerful, what aspect of object-oriented programming are we using here? It's not even really technically OOP, where one class is implemented in terms of another class. It's composition, right? Remember, we kind of did this with sorted list. We have an array, and then we surround that with an array list, and then we surround that with a sorted array list. Right? And so we can use this kind of a layering of abstraction and composition in order to get what we want. We didn't want an inheritance hierarchy there, because a list is not necessarily a sorted list, and a sorted list is certainly not necessarily a list, or vice versa. Right? Instead, we can always use composition to extend the functionality of something that we've built already, or that somebody has already built for us. And by the way, in practice, what should you do in practice? Actually, I'll save this for the end. In Java, use a deck. Right? And it is pronounced deck. It's not anything. It's not DQ. It's called a deck. A deck is a double-ended queue and allows you to use it either as a stack or as a queue or as some variation thereof. Okay. I'll see you next week.